Okay then, so today I want to do a few more examples, 3 examples of the geometric distribution with you before you go and do some on your own. So the first one we've got in a board game, it's necessary to throw a 6 with an ordinary die before a player can start the game. Part A, write down as a fraction, part A1, the probability of a player starting on the first attempt. It's a nice easy question. 1/6, yeah. Okay. We haven't been asked to write down any notation or anything, so that one is just 1/6. That's A1. A2, not starting until the third attempt. Now, before we go any further, let's decide what we are dealing with here then and start using the notation. What are we dealing with here?
That's a geometric.
Geometric distribution. Okay. What is the parameter?
3 a 6.
1/6, yeah.
1/6.
Okay, because that's our success probability. And let's say x then follows the geometric distribution. What is x measuring? X is the what?
Number of throws you have to do to get a 6.
Yeah, it's the number of throws to get. You need to put one more word in your definition. Somebody said here the number of throws to get a 6.
Up to and include.
Well, yeah, to also get the first 6, yeah. Number of throws to get your first 6. So in part A2, where it says not starting until the third attempt, if we're using notation,
X equals 3.
it's a probability, yeah, that x equals 3. Now, before we go any further, if we are doing the geometric distribution, we have a formula for the probability x equals r. What is the formula for that probability? Go on, a bit louder, Catherine.
1 minus b in a bracket
Yeah,
to the power of r minus 1 times p.
yeah, that's right, okay. It's a failure probability, r minus 1 times, and then that's followed by a success, so that's right. So over here, if we use that formula, we've got our probability of success. What calculation will I be writing down then here?
1 minus 6. 1 minus a 6 to the power of 2 squared times a 6.
Yeah, that's right, okay. My failure probability to the power of 2, and then by times by a 6. I can see some people tapping away on calculators already.
0.195.
Pardon?
0.195.
Just say the question, actually, write it down as a fraction.
31, 36, is it?
Yeah, I think it's 25 over 216. Because what you've got here is 5/6 squared times by 1/6. So times the tops you get 25, times the bottoms you do get 216, and that one won't cancel down. Okay. Part 3 said requiring more than 3 attempts before starting. Requiring more than 3 attempts before starting. How can I write that one down in notation?
Probability that x is greater than 3.
Okay. Now I'm going to look at this in 2 different ways, 2 different approaches to answering this one. Can anybody tell me one way of answering this question? Yeah.
We work with the probability that x is greater than or equals to 4.
Okay. So greater than 3 is 4 or more, and we could do 4 or 5 or 6. And what would we end up getting? An infinite thing. Yeah, infinite GP. Yep, that's right. Or
Could you do 1 minus x is less than or equal to 3?
yes, we could do.
Like
Okay.
the tables.
Are there tables for the geometric distribution in the book? No, there aren't. Okay. But we can do, I'm going to do the second method that was used first, which is the sort of simpler one possibly. Yeah, method 1 is to say, okay, well, I will just add some things up, but I can't add up greater than 3 because it does go on forever. Well, we will do that in a minute as an infinite GP. But turn it around. What is the opposite of greater than 3?
Less than or equal to 3.
Yeah, less than or equal to 3. Okay. less than or equal to 3, what probabilities are there we could have for less than or equal to 3? Can we have probability x is 0?
0.
No.
No.
1, 2, 3.
Yeah, you can't have probability x is 0 if you're geometric. You can't get a 6 on your 0th throw. So we can have the probability x is 1, which we've already worked out. The probability x is 2, which we haven't worked out. And the probability x is 3, which we have already worked out. We worked out this one a minute ago, was 25 over 216. The 1 we worked out in part 1 of the question was 1/6. Getting a 6 for the first time on the second go, can anybody just tell me what calculation I would write down for that? Maybe somebody who I haven't heard from so far?
1 minus 6 to the power of 1 times 1/6.
Yes, okay. Failure and success. Okay. 5/6 times by 1/6, what would that be?
36.
Yeah, that would be 5/36 in there. So I need to do a 1 minus that lot. Okay, nothing wrong with this method. We've already worked out 2 of these numbers. Has anybody done that and got an answer out?
Um, 91 over 216.
Now, I agree with the answer I heard to my right. 125 over 216 if you do it.
If you do 1 minus.
Okay. Yeah, when you do the 1 minus, that is what you get. Okay, so that's one way, perfectly valid way of doing it. But then method 2, the method that Jack said was to do it the other way around. Probability x is greater than 3 is the probability x is greater than or equal to 4. It might be easier or helpful to write it down like that. Am I going at an okay speed, or do I need to slow up for some people? Okay, so greater than or equal to 4 is the probability that it's 4 plus the probability that it's 5 plus the probability that it's 6, and that goes on forever. So dot 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 there. Jack, what will be the calculation for the x equals 4 one? Can you tell me the calculation for the x is 4 1?
1 minus 6
Which I'm going to write down as 5 6. Yep.
cubed
Yep.
times 6.
Okay. Grace, can you tell me the next one, please? The
1
x is,
minus 6
yep.
to the power of 4
Yep.
times 6.
Yep, that's right. And over here it'll be one more failure. And that is an infinite GP. So this is clearly the first term. So that is your A for your infinite GP. What is R for your GP? What are you
5, 6.
multiplying by each time? An
5,
extra?
6.
Yeah, 5 6. Okay. So we've got that. What is then the formula for the sum to infinity?
A over 1 minus R.
Yep, A over 1 minus R. So A was 5 6 cubed times by 1 6. 1 minus R is 1 minus 5 6. Can we spot anything here?
It's just 5 6.
The 6 and the 6 would cancel.
Yeah, that 6 there and that 6 there cancel out. So we are left with 5 6 to the power of a third,
Which is 155 times 260.
which is, thankfully, the same answer we got a minute ago. 125 over 216. So, can we actually generalise from this? And I think somebody mentioned this last lesson, maybe into a red box rule. The probability x is greater than 3 was what this question was. The probability x is greater than r. Can we generalise into a formula? 1 minus p to the power of r. Yeah, it was a failure to that r number. So yeah, so if you want, you can generalise and use that. I don't think it's given to you anywhere in the exam. If you want to remember it, you can do. So that was part 3. Part 4 of the question said, what is the most common number of throws? So those of you who got the worksheet, what's the most common number of throws somebody will make? Can anybody maybe rephrase that question in terms of, or including the word probability in it?
What's the highest probability of throws?
Well, yeah, certainly. You're looking for the highest probability and what x value went with it. What will be the highest probability? You'll have a probability for x is 1, probability for x is 2, probability for x is 3, and so on.
It'll be x is 1 because you haven't been in fact no,
You're right.
it's x is 1.
The most common number of throws, that is the same as finding the largest probability Now, we have actually got some of these worked out already. But when x was 1, we worked out the probability was 1/6, which as a decimal is 0.17 to 2 decimal places. When x was 2, we worked out the probability was 5/36. And I'll tell you as a decimal, that is 0.14. For x is 3, we worked it out to be 25 over 216, which I've got here is 0.12 as a decimal. Why is it that these probabilities are getting smaller each time, Beth?
Because you're timesing it by 5/6.
Yeah, that's right. Each time we are going down, we are timesing by 5/6, which is making it smaller. So the most common number of throws, the probability which is the largest is
1.
always 1. Yeah, it's in any case of this, it's always going to be 1. Because these numbers are always getting smaller as you go. So the most common number of throws, because it's a geometric, the answer is 1. Answer is 1, i.e. the first throw, or just having one throw rather. Just having one throw. So the most common result will be just having one throw. And for the geometric, that is always the case. For the geometric, the most common result will always be 1, no matter what p is. Because p will always be a 0-point number. Now, there's one thing I haven't taught you yet, which you need for part 5. Part 5 of the question said, what is the mean number of throws? Now, let's just think. We have got the probability of getting a 6 is 1/6. We want the mean number of throws. Does anybody have any ideas? Well, the average number of throws is to get a 6.
Would you have to do like, because there's no limit on how many throws you can do, would it be like the sum to infinity and then divide that by infinity?
Oh, dividing by infinity, that's going to be a bit problematic. Does anybody think, actually don't necessarily think geometric, don't think sums to infinity, just sort of think a bit of common sense maybe.
3.
We've got a 3, we've got a 6. We have heard the right answer.
3.
6.
6.
Throw 6 times.
It's 6.
Should get what?
It's 6.
shouldn't
Okay? You expect to get a 6 once every 6 throws.
Opposite is 6.
Okay? That's what 1/6 means, 1 in every 6. So the mean number of throws is 6. So there's a key thing here, red box rule. For the mean for any geometric distribution is always 1 over p. That is for geometric. So for our question, where we had p being 1/6, the mean will be 1 over 1/6, which is 6. So the mean number of throws is not the same as the most common number of throws, but then you've come across things before where the mode and the mean aren't the same. Right, the next bit of the question. What was the next bit of the question? Prove that the probability of a player requiring more than n attempts before starting is 5/6 to the power of n. Does anybody want to say anything before we do that bit? Because it's basically what we observed earlier on, isn't it? It's basically saying
X is greater than n.
it's this one here, isn't it? Okay? So we have really already done it. We can run through it though, because it says we've got to do it as a proof. So they say prove the probability that a person requires more than n attempts is 5/6 to the power of n, and that we have to prove. That is our command. So if they want more than, if they have to have more than n attempts, what's the first number of attempts they could have?
1.
Plus 1.
Yeah, n plus 1. Or they could have n plus 2. Or they could have n plus 3, and so on. We've got here p is 1/6 in this case. So of having a first success on the n plus first go, what calculation will go for this? Having your first success on your n plus first go. Beth?
5/6 to
Yeah, we need n failures and then we have our success. Over this one over here, Heidi, having our first success on our n plus second go, it'll be very much like this one but slightly different.
5/6 to n plus 1 times 6.
Yep, that's right. And then over here, it'll be your 5/6 to your n plus 2 times by a 6. So this is an example of a, anybody?
Infinite. Sum to infinity.
Yep, that's right. So there is your first term. And R is
N. N.
not n, 5/6. Yeah, it's what the n is the power of.
Right.
So the R is that, A is that, and we have a sum to infinity, and we said before that's A over 1 minus R. So if you bung those things into the formula, we have A over 1 minus R just like we had before. The 1 minus R, that's 1/6. That will cancel with that, and we are left with what we want, the 5/6 to the power of n. I'm going to stop the video there. The next bit I will do in a different video clip.